1968 National Electrical Code, or NEC, introduced the first definition and rule pertaining to ground fault circuit interrupters, commonly known as GFCIs. Specifically, this groundbreaking information can be found in Article 680 of the Code. To understand the significance of this inclusion, it's important to delve into the context of electrical safety at that time. Before GFCIs became commonplace, electrical shock hazards, particularly around water, were a significant concern. Appliances and electrical systems with insulation faults could create a path for electricity to flow to ground through a person, leading to serious injury or even death. The introduction of GFCIs marked a major step forward in electrical safety. A GFCI is a device designed to detect very small imbalances in electrical current. These imbalances indicate that current is leaking somewhere, potentially through a person. When a GFCI detects such an imbalance, it quickly trips, interrupting the flow of electricity and preventing a dangerous shock. Article 680 focused on specific applications where the risk of electrical shock was particularly high, notably around swimming pools. The environment around a swimming pool presents numerous opportunities for electrical hazards. Water is an excellent conductor of electricity, and people are often barefoot and in close proximity to electrical equipment such as pool pumps, lighting, and heaters. The 1968 NEC mandated the use of GFCIs in these high-risk areas to provide an extra layer of protection against electrical shock. The wording of the initial GFCI definition in the 1968 NEC is crucial. It defined the device, specified its operating characteristics, and outlined its intended function. This definition established a clear standard for manufacturers and installers to follow, ensuring that GFCIs met a minimum level of performance. The rule associated with this definition specified where GFCIs were required, providing clear guidance to electricians and inspectors. The impact of the 1968 NEC GFCI provision was profound. Firstly, it raised awareness of the dangers of electrical shock and promoted the use of GFCIs as a vital safety measure. Secondly, it spurred the development and refinement of GFCI technology, leading to more reliable and effective devices. Thirdly, it set a precedent for the expansion of GFCI requirements in subsequent editions of the NEC, gradually extending their use to other areas where electrical shock hazards existed, such as bathrooms, kitchens, and outdoor locations. Over the years, the NEC has continued to update and refine its GFCI requirements. The definitions have been clarified, the performance standards have been tightened, and the scope of application has been broadened. Today, GFCIs are an indispensable part of modern electrical systems, providing essential protection against electrical shock. The 1968 NEC pioneering work in introducing GFCI technology laid the foundation for these advancements. Understanding the historical context of the first GFCI definition and rule in the 1968 NEC provides valuable insight into the evolution of electrical safety standards. It highlights the importance of ongoing innovation and the continuous pursuit of safer electrical practices. It is a reminder that electrical safety is not static, but rather a dynamic field that evolves in response to new technologies, changing conditions, and a growing understanding of electrical hazards. Looking back at Article 680 of the 1968 NEC, one can appreciate the foresight and commitment to safety that led to the introduction of GFCIs. It is a testament to the power of codes and standards to improve the safety of our homes, workplaces, and communities. The 1968 NEC initiative to include GFCI regulations was a critical advancement in electrical safety, establishing a benchmark for future codes. Ground fault circuit interrupters operate by monitoring the balance of electrical current between the hot and neutral conductors in a circuit. Under normal circumstances, the current flowing through the hot conductor should be equal to the current returning through the neutral conductor. If there is a difference between these currents, it indicates that some of the current is leaking to ground, possibly through a person. GFCIs are designed to detect even small differences in current, typically as low as 5 mA. When a ground fault is detected, the GFCI trips, interrupting the circuit and stopping the flow of electricity in a fraction of a second, often within 25 milliseconds. This rapid response time is crucial in preventing serious injury or death from electrical shock. The 1968 NEC specified that GFCIs used around swimming pools must meet certain performance standards. These standards ensured that the devices were reliable and effective in detecting and interrupting ground faults. The code also mandated that GFCIs be installed in a manner that would protect them from damage and ensure their continued operation. One of the challenges in implementing GFCI technology in the 1960s was the relatively high cost of the devices. GFCIs were a new technology, and their production was not yet as efficient as it is today. As a result, the initial cost of installing GFCIs could be a barrier for some homeowners and businesses. However, the benefits of GFCI protection far outweighed the costs, and the code requirements helped to drive down the price of the devices over time. Another challenge was the lack of widespread understanding about how GFCIs worked and why they were important. Many people were unfamiliar with the concept of ground faults and did not appreciate the risk of electrical shock. Education and outreach efforts were necessary to raise awareness of the importance of GFCI protection and to encourage people to install and maintain these devices properly. The 1968 NEC GFCI provision was not without its critics. Some argued that the code requirements were too burdensome or that they were not necessary in all cases. However, the overwhelming evidence of the effectiveness of GFCIs in preventing electrical shock ultimately led to their widespread acceptance and adoption. Over the years, the NEC has expanded the scope of GFCI requirements to include a wider range of locations and applications. Today, GFCIs are required in bathrooms, kitchens, garages, outdoor areas, and other locations where there is a high risk of electrical shock. The NEC also specifies the types of receptacles and circuits that must be GFCI protected. In addition to the NEC, other organizations and agencies have also played a role in promoting the use of GFCIs. The Consumer Product Safety Commission, or CPSC, has issued safety standards for GFCI devices and has conducted public awareness campaigns to educate people about the importance of GFCI protection. Insurance companies have also encouraged the use of GFCIs by offering discounts to homeowners who install them. The evolution of GFCI technology has been remarkable. Early GFCIs were relatively large and bulky, and they could be prone to nuisance tripping. However, modern GFCIs are much smaller, more reliable, and less likely to trip unnecessarily. They also incorporate advanced features such as self-testing and ground fault indication. One of the key advancements in GFCI technology has been the development of electronic GFCIs. These devices use electronic circuitry to detect ground faults and to trip the circuit. Electronic GFCIs are more sensitive and faster acting than their mechanical counterparts. They also offer greater immunity to nuisance tripping caused by electrical noise or other disturbances. Another important development has been the introduction of arc fault circuit interrupters, or FSIs. FSIs are designed to protect against fires caused by electrical arcs. Arcs can occur when there is a loose connection or damaged wiring in a circuit. They can generate intense heat, which can ignite nearby flammable materials. FSIs detect the unique characteristics of electrical arcs and trip the circuit to prevent a fire. The NEC now requires FSIs in many residential circuits, in addition to GFCIs. The combination of GFCIs and FSIs provides comprehensive protection against electrical shock and fire hazards. Properly installed and maintained GFCIs are essential for electrical safety. It is important to test GFCIs regularly to ensure that they are functioning properly. Most GFCIs have a test button that can be used to simulate a ground fault. When the test button is pressed, the GFCI should trip, interrupting the circuit. If the GFCI does not trip when the test button is pressed, it should be replaced immediately. It is also important to inspect GFCIs for any signs of damage, such as cracks or discoloration. Damaged GFCIs should be replaced immediately. When replacing a GFCI, it is important to use a device that is listed by a recognized testing laboratory, such as Underwriters Laboratories, or all. Listed GFCIs have been tested to meet safety standards and are more likely to perform reliably. In addition to installing and maintaining GFCIs properly, it is also important to practice other electrical safety precautions. These include avoiding the use of extension cords, keeping electrical appliances away from water, and never touching electrical wires or components with wet hands. By following these precautions, you can significantly reduce your risk of electrical shock. The legacy of the 1968 NEC GFCI provision is still felt today. GFCIs have saved countless lives and have prevented numerous injuries. They have become an indispensable part of modern electrical systems. The ongoing development and refinement of GFCI technology will continue to improve electrical safety for years to come. The principles behind GFCI technology extend beyond residential and commercial applications. They are also used in industrial settings to protect workers from electrical hazards. For example, GFCIs are commonly used in construction sites, factories, and other industrial facilities. In these settings, GFCIs are often used to protect portable electrical tools and equipment. The use of GFCIs in industrial settings can help to prevent electrical shock injuries and fatalities. The NEC provides specific guidelines for the use of GFCIs in industrial applications. These guidelines cover topics such as the types of equipment that require GFCI protection, the location of GFCI devices, and the testing and maintenance of GFCIs. Compliance with these guidelines is essential for ensuring worker safety. GFCIs are not a substitute for other electrical safety practices. It is still important to follow all applicable electrical safety codes and standards, even when GFCIs are present. GFCIs are intended to provide an extra layer of protection, but they cannot eliminate all electrical hazards. A thorough understanding of electrical safety principles is essential for anyone who works with electricity. This includes knowledge of topics such as grounding, bonding, insulation, and overcurrent protection. Proper training and education are crucial for preventing electrical accidents. The National Fire Protection Association, or NFPA, offers a wide range of training courses and resources on electrical safety. These courses cover topics such as the NEC electrical safety in the workplace and electrical safety for homeowners. The NFPA also publishes numerous standards and guides on electrical safety. Continuous learning and professional development are essential for staying up to date on the latest electrical safety practices. The electrical industry is constantly evolving, with new technologies and techniques being developed all the time. It is important to stay informed about these changes and to adapt your practices accordingly. By embracing a culture of continuous learning, you can help to create a safer electrical environment for yourself and others. The history of GFCI technology is a testament to the power of innovation and collaboration in improving electrical safety. The 1968 NEC GFCI provision was a groundbreaking achievement that has had a lasting impact on the electrical industry. The ongoing efforts to develop and refine GFCI technology will continue to protect people from electrical shock hazards for years to come.